Right. So we are going to look into this example now. Okay, we are going to view into this example. So this example is basically a simply supported beam, right? So we're going to determine the shearing stress at point A and then at point B. But this question has a lot of layers. Okay, I'll explain to you what do I mean by a lot of layers. So what I've done down here is I've created an image of the rule, okay, which we will apply in our analysis. Okay, so I'm going to apply all these 4 rules today, and you guys will then appreciate it. Okay, so if you look at this cross section, it looks like, oh, it is so confusing now, isn't it? You look at it, where am I going to take the area? What area am I going to take? So on and so forth. Okay, so don't worry about it. So let me highlight what you are going to see in this example. Okay, there's a few four. So the procedure is we are going to draw the free body diagram. Okay. Then next, so the next thing that we're going to do, we're going to determine the reaction at A and at point B. Then I'm going to sketch the shear force diagram. So there are a lot of layers down here, okay? So that's why I say this is a long example. I'm going to sketch my shear force diagram, and myself do it now. I'm going to do my bending moment diagram. Just an introduction. Later on, after this class, we are going to look into bending, okay? Bending moment. Some of you have done it before. Some of you have not seen it yet. Don't worry, I'll give it up. Then from here, we are going to find the second. We are going to determine the shearing stress. So to determine the shearing stress, we need to find the centroid. Okay, we need to find the centroid. We need to find the second moment of area. Then we need to find the first moment of area. Okay, find the first moment of area. Then I'm going to do something further. Okay, we're going to look into the shearing stress distribution equation. Then finally, we're going to look at the shear stress at point A, and then we'll find the shear stress at point B. So this question alone, as I said, has a lot of layers. Okay, so the only thing that some of you are not sure is probably the part where it's regarding the shear force and bending moment diagram, because some of you might not have seen it in your college, depending on the diploma that you have. Okay, let's draw the free body diagram first. Okay, so let's construct the free body diagram. So free body diagram. So you draw up your transformation, and then we have our rotation about Z. So this is how I'm going to define. This is how I'm going to define our structure, right? So we're going to draw our free body diagram. In 2D first. So we have point A, then on the other side point B. So this is AY, and this is BY. And then we know that we have a load coming down here, smack on the center at 180 kilonewton. Okay, we have it at 180 kilonewton, and we are aware that we have our respective distances. So this is equal to 0.5 meters, and then this is 0.5 meters. Okay, so we realize that that we can first do static analysis where summation of forces in the y direction is equal to 0. So we know that AY plus by BY minus 180 times 10 to the power 3, the whole thing is equal to 0. Then you can declare that based on symmetrical loading and geometry about the y-axis, right? We can declare that AY is equal to BY. Okay, so the first equation over here, I'm going to call it our equation number 1. So from here, we know that, okay, we're going to substitute AY equal to BY, we're going to substitute into equation number 1. So what we have is 2AY is equal to 180 times 10 to the power 3 Newton, or times 10 to the power 3, and AY is equal to 90 times 10 to the power 3 Newton, and this is also corresponding to your BY. Okay. So next, I'm going to construct our shear force diagram. Okay, we're going to construct shear force diagram. So this is your V, this is your 0, this is your 90, and that's your minus 90. And then we have our X distance. Okay. So over here, our 0.5 meters, and then down here, 1 meter. So over then I'm going to label this is our point A, and then over here there is our point B where the 1 meter is. So when we draw a shear force diagram, it looks like this. Okay, it will come to here, then it'll come down. So it'll come down. So it is 90 initially, right? 90 initially, right? Then it will drop itself down by 180. Okay, I do apologize, my bad. It will come down by 180 kilonewton. So the V over here is in kilonewton. And then it will move across. Okay. And then it will bring itself back to positive 90. So you go back to 0. Okay. So what you see down here, we just found that Vmax is equal to 90 times 10 to the power 3 Newton. Okay. Right. We just found this out by looking at our shear force diagram. It's not, the shear force will not be any higher than 90 at all, or will not be any lower than minus 90. So we're looking at the magnitude. Vmax is equal to 90. So then we look into our bending moment diagram, right? So the bending moment diagram, which I'm going to introduce. Don't worry, you have not seen this before. Okay, some of you are like, oh, I've not seen this, but don't worry about that. Okay, I'm just going to introduce what you can see in the near future. Basically, that's it. Okay, and then over here, this is your X. We're going to focus more on the positive, right? It's because this is more positive bending moment. So this is M, and it can be kilonewton, kilonewton meter, right? So likewise, at the midpoint, it's equal to 0.5, and then over here, it's going to be 1 meter. So what you'll see is that over here, you're going to see straight line going straight up. There's your bending moment. And then after 1, it will come down. So this is your bending moment diagram. And the maximum will be equal to 90 power 3 multiplied 0.5 will be equal to 45. Okay, kilonewton meter. Okay, so that is your, so what we have down here, we have just constructed our bending moment diagram. Okay, where Mmax is equal to 45 times 10 to the power 3 Newton meter. So when we select our structure, right, we will select later on our probably after term test 2, we'll merge the shear force, the stresses inducing by the shear force and the stresses inducing by bending moment by using Mohs circle. That's what this topic is all about. We combine all the loading structure into one, and then we can select the proper structure for it. You cannot just look at the shear force, ignore the bending moment, neither can you look at the bending moment and then ignore the shear force. Okay, so now, so what we have done is we have done this, we have drawn, we have done this, we have done this. So next, we're going to focus on the shear stresses now. Okay, so I'm going to divide my page into 2. We're going to look at the shear stress. Right. So the shearing stress we need to know what we are trying to identify. Okay. So if this structure, right? So if I draw down here, this is my X, my Y, and this is my rotation valve Z. So what we want to find down here is we want to find the shear stress acting on the X plane Y direction, right? If you cannot visualize this, so we just draw the cube again. Okay, we just draw the cube again. Right, and then if this is our shear force acting in this direction, and then if we were to draw our transformation, this is X, this is Y, and this direction is Z. So we know that over here, this space over here is your what? Is your X plane. So sorry, I shouldn't have done that, make it real messy. So we are looking at the shear stress in this direction. So this is shear intersecting the X plane Y direction, and this will go opposite. Wrong arrow type. And over here, this will be your shear in your Y X direction. And we know that this is shear XY is equal to shear YX. Okay. So from here, the shear XY is equal to VY over what? Right? VY over IZZ QZ multiply by what? Thickness. And what did I say? Okay, what did I write? Oh, it's just me. There is a lag. Okay. So what did I say earlier? So we are going to apply